Okay, so we discussed a few strategies in which cooperation may be sustainable in the case of a prisoner's dilemma game. And now what we'll try to do is to see what kind of discount factor we need in order to actually be able to sustain these strategies. The first thing we'll consider is the grim trigger strategy in this game. So, according to the grim trigger strategy, the idea behind that is that both players will cooperate until one of them defects, and if that happens, then they defect forever. So, let's say that player 1 plays the grim trigger strategy and we're considering player 2's incentives. So S1 is equal to C if B2 has always cooperated and D otherwise. We wrote it out more formally earlier. Right now I'm just writing it out in English. Okay, let's say this is player 1's strategy. Then player 2 knows that if she ever deviates, then the best she can hope for is 1-1, is to earn just 1 unit in every period in the future. So for player 2, what she's comparing is a stream of payments that is 2, 2, 2, 2, and so on, to a stream of payments which is 3, because she deviates once, and so she gets that, she gets to this cell where she gets 3 and player 1 gets nothing. But then after that, it'll just be 1, 1, 1, and so on. Right, if you're thinking Russia and Saudi Arabia, Russia can benefit initially, until Saudi Arabia has reacted, Russia can benefit by overproducing oil and selling more oil at a higher price. Like getting this, but Russia can't do that forever. So as soon as Saudi Arabia realizes that Russia is overproducing oil, Saudi Arabia will react by also overproducing oil, and so then both of them will end up getting 1. But in this case, we're just considering Russia's incentives, given that Saudi Arabia is playing this strategy. So this means an average, the average discounted payoff equals 2, and here the average discounted payoff equals 1 minus delta times 3 plus delta on 1 minus delta for neutron. Which is equal to 3 minus 3 delta plus delta, 3 minus 2 delta. And so Russia would prefer to cooperate only if 2 is a greater number than 3 minus 2 delta. So if 2 is greater than 3 minus 2 delta, then Russia will cooperate. This simplifies to 2 delta being greater than 1, or delta greater than 1/2. Actually, if they're indifferent, then also you have cooperation, so 2 has to be at least as large. And so cooperation can be sustained with a grim trigger strategy as long as delta is greater than 1/2. So if you have a delta, let's say 0.6, and as Russia, you know that Saudi Arabia is playing a grim trigger strategy, then you will cooperate with Saudi Arabia. Hope this is clear. If it's not clear, ask me during the Zoom lectures. What we are doing is we are comparing the stream of payments where one, you cooperate, two, a stream of payments where you don't cooperate, and then you get the punishment which is prescribed in these different strategies. Okay. And as long as the payoff that you would get from cooperation is greater than the payoff you get from not cooperating and then getting punished, then you would cooperate. So we've talked about grim trigger. Let's now talk about limited punishment. Let's say you have k periods of punishment. So in the earlier video, what we saw was a 3-period of punishment type of strategy. That's what we described. But let's say it's just some random k periods. K is a number, a natural number that's chosen, and that both players know about. If it's k periods of punishment, then the stream of payments that you're comparing is 2, 2, 2, and so on, 2, 3, and then k periods of punishment, so that's 1, 1, 1, 1. There will be k of them, and then you go back to cooperation. Right? So, in that sense, this part is the same in both streams of payments. So we can ignore this. So what we're basically comparing is 2, 2, 2, k plus 1 times 2, 3, 1, 1. Where you get this k times and then that is once. And you also have to discount these, so this involves the sum of a geometric sequence, because you're adding 2 to 2 times delta to 2 times delta square up to 2 times delta to the power k, and here you're adding 3 to delta to 1 times delta square, which is delta squared, to delta cubed, to delta to the power 4, up to delta to the power k minus 1. Oh no, delta to the power k, because this started with delta to the power 1 here. And so this simplifies to 3 times 1 minus delta, so the average of this when we do 1 minus delta times this, we get 3 times 1 minus delta plus delta times 1 minus delta k. And here we just simply get what we're doing is 1 minus delta times 2 plus 2 delta plus. And so, cooperation is sustained if 2 times 1 minus delta to the power k plus 1 is at least as large as 3 times 1 minus delta plus delta times 1 minus delta to the power k. And that simplifies to delta to the power k plus 1 minus 2 delta plus 1 is less than or equal to 0. Delta has to be large enough that this holds. If this holds, then this stream is smaller than this stream. It's worth less to the agent than this stream of payments. When so we can calculate this numerically. When delta is 2, this is approximately 0.62, and when delta is 3, this is approximately 0.55. As you, when k is 2, this is delta cubed. We can solve this numerically. So when you have just 2 periods of punishment, then delta is 0.62. If you have just 1 period of punishment, then basically k is 1. This becomes delta square minus 2 delta plus 1, and that is never strictly less than 0. It's only going to be equal to 0 with delta equal to 1. When you have 2 periods of punishment, k equals 2, then you can sustain cooperation for any delta that's greater than 0.62. When you have 3 periods of punishment, you can sustain cooperation for delta that is greater than for any delta that's greater than 0.55. And as you increase the number of periods of punishments, you begin to approach delta 0.5, basically delta 1/2. So you begin to approach the level of patience which you needed as a threshold to sustain cooperation when you had infinite periods of punishment. Excuse me for 1 second. And then finally, let's look at the tit-for-tat strategy. So right now we're assuming that player 1 plays a tit-for-tat strategy. So player 1 will cooperate if player 2 has cooperated in the previous period, and player 1 will defect or deviate if player 2 has defected or deviated in the previous period. We just finished this. Now we're doing this. And so player 2 can have, if player 2 defects, and player 1 defects, and player 2 just continues to defect, then player 2's stream of payments will be 3, 1, 1, ad infinitum. Unless player 2 decides that she's going to cooperate and then bring the situation back to a cooperative regime. Cooperation, as always, gives you just 2, 2, 2, 2, 2, because player 1 will keep cooperating as long as player 2 keeps cooperating. The other alternative is that player 2 just switches between C and D. Right? If you keep switching between C and D as player 2, and when you're playing D, you get 3, and then you switch to C, you get 0, and then you play D again, you get 3, and you can switch to C, you get 0, and so on. So that is also a valid choice by player 2. And we'll see what each of these is worth. In order for cooperation to be optimal, it simply is enough if this is greater than defecting once and defecting forever, and it's greater than doing this switching kind of strategy. Okay. So this yields an average payoff that is 2. This, as we calculated earlier, in the case of the Grim Trigger strategy, yields an average payoff that is 3 times 1 minus delta plus delta. And this yields 1 minus delta times 3 divided by 1 minus delta square, which is 3 divided by 1 plus delta. Let's just compare these two for a second. 3 times, so this is basically 3 minus 2 delta. If we multiply this by 1 plus delta in the numerator and denominator, we get we can do this. We would get 3 plus 3 delta upon 1 plus delta minus 2 delta. That doesn't seem to work. Okay. So what I need is for 2 to be at least as large as 3 divided by 1 plus delta, which means that 1 plus delta should be at least as large as 3 divided by 2, or delta should be at least as large as 1/2 in order for this stream to be better than this stream. And comparing this here, 3 times 1 minus delta plus delta should be less than or equal to 2. 3 minus 2 delta plus 2 delta should be greater than or equal to 1, delta greater than or equal to 1/2. Okay, so as long as delta is greater than 1/2, cooperation is sustainable even with a tit-for-tat kind of strategy. Because as long as delta is greater than 1/2, you're better off cooperating than deviating once and then coming back. Deviating once and then just getting 1 forever. And you're also better off than you would be if you just deviated for 1 period, then cooperated while the other player is deviating, then deviated while the other player is cooperating, then cooperated while the other player is deviating, and so on. And again, as long as delta is greater than 1/2, you'd much rather just get 2 in every period. And also, yeah, I think this is it. If you have any questions again about this, then we can talk during the Zoom lectures. Yeah. See you in the next video.